Just 1 minute.
Okay, Barbara, I tried to make it, but you are already.
Perfect. Yeah, now it works. Now it works. Then share screen. Yes. So sorry for this.
So it's the wrong screen. Yeah, now it's the right one.
Now it's the right one. Do you see it now?
Yes, excellent.
All right. Thank you very much, and sorry for this. Sorry for this small technical issue. So yeah, welcome everyone. I'm really delighted to be here and be able to talk to you in the second ELLIS NLP workshop. I very much enjoyed also the first edition, so thanks a lot for giving this opportunity. And today I want to talk about an issue that we all know about, and it's everywhere, but we often kind of don't tackle it. So would like to bring this to your attention. And so, in fact, if you think about human annotation projects, you all have probably carried out annotation projects because they are really at the core of the data that we are learning from. And we all know that disagreement in human annotation is essentially everywhere. But often we try to aggregate the annotations to come up to one gold standard. And in this way, we actually don't look at so much at these disagreements. So the question is, can we actually see this disagreement as a side benefit of annotation, or a sort of fortuitous data that's out there that we often just don't make use of? So the big question that I'm addressing in this talk here today is disagreement a source of information? Can we exploit it? If so, how? And what sorts of issues come up when we are trying to deal with this notion of disagreement? I'd like to point out that this is not something new. This has been known for a very long time, but we typically don't look into it so much. So in the rest of the talk, I structure it into 3 parts, as I would like to talk about 3 essential areas where disagreement factors in. And the first is, first and foremost, the data itself. Is disagreement actually just random noise? So we need to look at whether there is actually a signal in order to be exploited later on. So this is kind of the prerequisite that we need for the rest of the modeling and evaluation. And in fact, in the second part of the talk, I would like to go into a little bit summarizing what has been done on modeling disagreement, or how can we actually leverage disagreement, and show you also one recent case study that we have been doing, proposing one new way on using disagreement. And in the end, I would like to touch upon a very important aspect, namely evaluation. We also just heard from Thomas that evaluation is a big chapter, so I will want to go into evaluation a little bit. This is in fact a big chapter also for disagreement-based approaches, where we will see there is still a lot to be done in that area as well. But the big question there is, how can we actually evaluate our models in light of disagreement between annotators? All right, then let's have a look at the first act, namely the data. So in this part, I'm looking at selected examples to give you a little bit an idea of where has disagreement been noticed and how does it look like. So here, for example, is an example from the medical relation extraction task. This is from work that dates back, for instance, by Laura Arroyo and Chris Welty, but also by Balomaki. And this has been one of the areas where disagreement has been also taken as a signal, effectively. Here we have a sentence: these data suggest that this riboflavin deficiency that may be related to some dietary intake of this medicine, riboflavin. And if then what has been noticed, if you give this sentence to annotators, even expert annotators, and ask them to derive the relation between the 2 highlighted terms here, then you get a distribution of what possible relations, for instance, associated with, or symptom or causes. So some of which are really rather plausible, some of which are less plausible, right? So but you do observe that there is a large variety of answers that you get back. Another example where disagreement has been looked at quite a bit is in fact recognizing textual entailment. And here, or nowadays, even called natural language inference often. This is an example from the original data that dates back to Ida Dogan, which has been recently re-crowdsourced by Ellie Pavlik. And what the task here is, okay, given a premise, is the hypothesis entailed? So, for instance, here is an example from the data. Amanda carried the package from home, and the hypothesis is Amanda moved. And if you look at the original data, this was specified as an entailment. But now, if we look at the distribution that the Ellie Pavlik got by re-crowdsourcing the data set and asking 50 annotators, you see that a lot of the annotators say also this is entailment, but it doesn't look so clear, right? There's also some that say there is, whether carrying the package home entails moving is not so clear, or even might be contradictory. So there's a lot of disagreement here in this example, for instance. Another, we looked now at the semantic task, but what about syntactic tasks? And in fact, we can also find disagreement in, say, dependency parsing annotations. I'm showing here two examples. On the right, we see a Norwegian example that was annotated. Yeah, this was on a study some years back, where we see where the adverb is, it's not so clear where it is attached. But we also see here an example from the Liu et al. Study, which annotated Twitter tweets with universal dependencies. And here, actually quite fitting on the topic right now, which is the Olympics, right? The question is whether there is the zero copula reading, or there is this noun, clause modified noun, and depending on which, there are two plausible dependency annotations. So we moved now from more semantic tasks to syntactic tasks like dependency parsing. But what about even simpler, presumably simpler syntactic tasks like part-of-speech tagging? And we've seen that in fact there are linguistically hard cases even for part-of-speech tagging. There's a very nice paper by Chris Manning from 2011, for instance, who looked at what does it take to go from the 97% to the 100, and is it time for some linguistics? So there are very really concrete examples of cases where it was very hard to determine a concrete right part-of-speech tag. So another example here is from data by, again, tweets, where we have asked crowdsourcers to re-annotate tweets. And this is yet another example where you see anything has been annotated with a noun, pronoun, or adjective. So there is also disagreement in these post tags. So having shown you these examples, now the question is this actually just, are these disagreements randomly distributed? Or can we estimate these disagreements from presumably small samples even? And so this is something that we looked at some years ago, where we collected doubly annotated part-of-speech tagging information from different domains. And what we found is that there are consistent disagreements between different domains. For instance, you see here two confusion plots from the Wall Street Journal on the left side and the Twitter corpus on the right side. And there are disagreements, for instance, commonly like adjective noun confusions or particle apposition confusions that we found were across domains stable. But there are, of course, also some of the disagreements which are more domain specific, like particularly in this Twitter example here. But overall, it looks like they are not just randomly distributed. So we can actually use these small samples in order to estimate at least these global confusion matrices to get an idea of where are disagreements on the tag level overall in the data. And another take on this is, in fact, a study by Ellie Pavlik, which looked at, okay, now, if we have seen that they are not noise, right? They are not randomly distributed, but can it still be the case that they are just unimodal? Can we model them with a single Gaussian distribution, and would that capture the disagreement? Or is this disagreement actually something more inherent in the annotation? And so the question they posed is, can we model the single ground truth with a unimodal distribution where the true label is the one in the middle, so to say. The mean represents the truth, and the variation is capturing the disagreement. Is that enough, essentially? And what they did is they re-annotated around almost 500 sentence pairs from the recognizing textual entailment task, and then analyzed this by looking at, okay, can we model it with a unimodal distribution, or are we better off if we take a distribution with multiple components? And what their study shows nicely is, in fact, that there are distributions or examples where one unimodal distribution is not enough. So here, for instance, is two examples from their study, which shows that you see the dotted line is the unimodal distribution, but you would be better off in modeling it with, say, a two-component Gaussian mixture distribution. And this shows that there is this kind of bimodal human judgment distribution in this data set. Now, the question is, how frequent is this? Because we all know that, you know, for some cases, there is little disagreement. It's very clear what humans agree upon, but how much of this data set, for instance, was actually better modeled with multiple components? And so they found, for instance, that by plotting the sentence pairs and the component weights, they found that approximately 20% of the sentence pairs do have a non-trivial second component. And this is, in fact, I think this is a very nice study, and really nicely shown that, you know, disagreement distributions are not unimodal, at least not for this task, and they contain inherent disagreement signal. So given this evidence, now the question that comes next is obviously, okay, what can we do about it, right? And I would argue that, you know, maybe it's time to just accept that there is inherent disagreement, and we are better off in actually embracing it in modeling. So, but in the overall literature, if we look at what has been proposed, there are a variety of methods which we can approximately summarize into two big strands. One is, okay, we actually want to filter the data. We want to keep the data where annotators are highly agreeing on the right label. And we want to disregard or filter out the data where there is very low agreement. The alternative, in a way, is to instead say we want to embrace this disagreement and exploit it into modeling. And so to summarize these two big strands, what I'm plotting here is a little overview of possible ways of learning with disagreement. So if you have human disagreement, in fact, the first strand would say, okay, let's resolve it. Let's try to aggregate it to a single ground truth, or filter out cases where we see large disagreements. And these are in fact two prominent approaches. So especially the first one, right, which you typically take that aggregation methods like Davidson-Kuhn, or even majority voting or weighting approaches to aggregation are taken into consideration. An alternative is in fact to say, okay, now we want to filter first data, and that has been proposed, for instance, by Reitzemann, Van der Acker, or by Klebanov et al., to focus more on learning from the high quality annotation data. The alternative instead is, okay, let's look at embracing this disagreement. And here, if you think of the possible ways, we can at least come up with two broader subparts, which are, for instance, okay, we can say, let's directly learn from the disagreement, right? We can see that as a distribution, and we can directly learn from the disagreement distribution instead of first aggregating it, for instance. Or there is this middle ground where you still assume that there is a gold and a single label you learn from, and then you augment it with disagreement information. And so here, for instance, a couple of approaches which have been explored are in the augmentation world, that you essentially take small agreement samples and then weight your examples by this disagreement, or multitask soft loss. And I will get into these two approaches in a second, actually. Alternatively, there are approaches which have been proposed to directly learn from the distribution, where you, for instance, directly learn from the soft labels, or there are other approaches which for instance, try to add different layers to model the crowd, or simply assuming that you repeat the labels with different labels and take that as an approach. But in the rest, I will go briefly into the third part, this augmentation, where you take disagreement as kind of an additional signal in learning. And this is something that, for instance, we have proposed some time back in 2014 with De Koya and Osoro, where, okay, the idea here was, what if you have, some small amount of data where you have doubly annotated data, and then you can estimate the confusion from the small amount of data and use this as additional, confusion matrix or confusion between the labels in learning. And what the main idea here is whenever your model predicts a label where humans also don't agree on, then you update your loss less. So you learn actually by including this global view. You say, okay, globally these labels have been confused, and we also learn to rely less on these confusions when we train the model. But recently we also thought, okay, data sets where the raw labels become available are being increasingly released, luckily, and we're very happy to see this. But can we actually also, instead of directly learning it, can we use multitask learning in order to exploit this disagreement information? So this is a recent study where instead now of assuming we have a small sample of data, we assume now that for our data set, we have multiple human annotations. So we have access to the raw annotations. And normally we would take the aggregate, right? We would take either the majority vote or David Skeen weighting. So we want to derive a single goal distribution. And now in this study, we were asking, okay, typically we then disregard the left side and we train our model on the right, but can we actually use multitask learning to embrace the disagreement information from the raw annotations into modeling? So this is then the model that proposed recently, that normally you learn a model on the gold data, then you observe, say, your softmax distribution, and then you observe the gold label and you backpropagate the loss given this single gold label. And instead, in this work, what we proposed is to simply augment it with a soft label loss. So you do the same as before. You are still learning on the gold label distribution, but now you also look at, hey, how does the predicted distribution actually relate to the annotated distribution? And now the question is, okay, how do we measure this disagreement? There are several ways. You could just look at the cross entropy between the two. But what we proposed here is, in fact, taking the predicted and the annotated distribution and measure the divergence, for instance, like the Kullback-Leibel divergence between the two, which is related to the softmax cross entropy. So how did this work? We did compare now the model which didn't use the soft loss auxiliary task with a model that did use the soft loss auxiliary task, and we looked at multitask learning with both gold and the majority votes, and then integrate the soft loss as an additional training signal. We tried this on 2 NLP tasks in this paper, but we later extended it to many more tasks. And we looked at path of speech tagging again, and there was also a data set where it's about binary stemming detection, essentially. And what we saw is here, these two plots summarize our main results. So we see that for both tasks, so for POS, we had 2 setups. We see on the left side the single task learning setup, and then on the right, the multitask learning setup. And what we saw is that in both cases, we saw significant improvements by integrating this auxiliary loss. And there was actually, if you swap the direction, that was a little bit better than just plain direct Kullback-Leibel divergence. But in both cases, we saw an improvement over the single task loss. But now, this is just 2 examples from this big strand, right? I've plotted before. So recently, we looked at all of these 4 directions in more detail, and there's a survey actually coming out. And we looked at these 4 directions with evaluation across also both NLP tasks and computer vision tasks, because quite some of this literature comes from, for instance, Peterson et al. Comes from the computer vision direction. And but we'll just summarize briefly some of the key findings. So we saw that filtering the data was essentially always worse. So you're better off in just aggregating all of it, or taking some distribution into modeling the distribution into account. But we saw also that directly learning from the distribution itself is not always very helpful. So we noticed that, for instance, on the CFAT-NH dataset, which has quite high number of annotators and of good quality, so the raw agreement between the annotators is quite high, then directly learning from the distribution was very helpful. In the other cases, overall, we though saw that this multitask learning with the soft loss, so augmenting the goal with this disagreement labels, was very effective. It was one of the most beneficial methods here, outperforming also the previously proposed weighting approach. But so I come now, after having introduced data and modeling, now I'm coming to the last chapter, namely evaluation. Because if you noticed in the plots before, we still used F1 score and accuracy. I think I plotted just one here, but in the paper we used F1 and accuracy, so that we still assume kind of the same kind of setup as we always do in learning, right? And this brings the question, of course, okay, how do we evaluate in light of disagreement? Because now we're training the model and let it, stay away from where humans also disagree on, but then we evaluate it still against the single ground truth. So there's kind of a discrepancy here, right? So what can we do about this? And in fact, we have an upcoming position paper at the benchmarking workshop where we argue that we really need to look more into this issue, that disagreement should also be considered into evaluation. And why this? Because if we look at the literature, a single correct answer ignores quite a bit of subjectivity and complexity of tasks, right? We very much like evaluation metrics, which are easy, understandable, and there's low risk of also getting evaluation wrong, which is fine, right? But it neglects the fact that we have these disagreements. We have seen in the first part that they are inherent, and we often don't make use of them and don't look at them. So, in fact, even works on learning from disagreement, including my own, has often still assumed a single ground truth in evaluation. So there is something to be done in this direction. In fact. So here's yet another example from a visual question answering dataset. So this is a picture from MS Coco, and there is the question of what is the background metal structure? And if you now look at the answers that you get from 10 annotators, you see that, yeah, well, there is a lot of them say platform, but there are also others that say, okay, station, roof, shelter, right? So what is then correct in this example, for instance? So often, in fact, these gold labels are a little bit of an idealization, and we have this disagreement which is not easily reconcilable. In fact, if you think about it, it's a complex topic, right? Because where are the sources of this? Why are we observing this disagreement? One is, in fact, the stimulus itself. It can be the ambiguity of the language, or the difficulty, or even poor annotation guidelines in the worst case. But also individual differences, right? There is also especially if you move to very subjective tasks, which I haven't touched on here, there is also work on more social computing related directions like hate speech. What is ground truth in hate speech, or for example, right? But then another dimension factors in, and that's the context and the attention of the annotator. We can also see that if we do annotation over time, that there is also, sometimes we even don't agree with ourselves, or there is also attention slips that come into play, which play an unintelligible role, in fact. And so what we here advocate for is like, okay, there are, we see that there are linguistically debatable cases in a majority of the cases, and there is other work in this direction which argues for this, like Jamieson and Gurevich has also shown or looked at whether this agreement is noise or actually additional information, or the crowd truth work by Arroyo and Welty. Palomaki, for instance, argued that there is a range of acceptable variation. So looking at certain instances which are more where variation is really acceptable, where certain other instances it's clearly errors. And there is also work by Uma and Basile on software relation NLP. But while there are these positions which are similar to ours, there's also a contrast work that advocate, for instance, to eliminate biases and try to neglect disagreement in annotation. And or I even heard about disagreement, filtering out the disagreement cases completely in order to focus on high quality good data in a way in that sense. But what we here propose, in fact, is let's not just evaluate, first of all, let's study this disagreement more, but in terms of evaluation, it's going to be important to evaluate both against the hard and the soft labels. And why that? Because hard labels is what we do, we assume a single ground truth. Soft labels are uncertainty of human annotators, or even like the opinion of the human collective, you could say. And so how can we do this? Well, there are many ways. For instance, you can take the Jensen-Shannon divergence between the predicted and the goal distribution, which has been tried out recently, for instance. But you could also just look at directly at the cross entropy, which has been tried, for instance, in image classification or also in NLP. But there is more. So we studied various hard and soft evaluation metrics in this upcoming survey, and it's a bit difficult to find. This is the single best software label metric. They of course are also correlated, but we need more work in this direction. And so this brings me already to the end of the talk. So I hope I have convinced you that not all disagreement is noise, and it might be very fruitful to actually embrace it during learning. Another implicit message is if you are working on an annotation project, please consider also releasing the raw annotation. But I would argue that this is still a lot of work needs to go into this direction, especially if you think about these sources of a disagreement and how to understand what are the sources of a disagreement and how to embrace them into evaluation. That's a big thing to do. If you're interested in this, I would like to point you also to the Semival 2021 Shared Task 11. It has finished, but the data and base models are still there. So this could be a starting point to look at into this direction. And with that, I thank you a lot for your attention, and I'm looking forward to your questions.
Thanks a lot, Barbara, for your very interesting talk. And we already have several questions. So the first one is from Andre. Isn't multitask learning of gold label plus disagreement with cross entropy losses equivalent to label smoothing, where the smoothing uses the disagreement distribution? Yeah,
this is a good question. Yeah, there is a relation, right? Because there is a relation to this, definitely. The only thing is that the label smoothing would be constant across the instances, right? As far as I know. But here, yeah, you could see it as a way of relation to label smoothing, but on an instance basis. So in this work, we really assume that we have per instance the distribution of the labels. And so it's kind of a label smoothing, human smoothing, so to say.
All right, thank you. So question number 2, is there any data correlating disagreement and annotator quality or vagueness of guidelines? The example from VQA with trees is characteristic. I would imagine that we separate and remove trivial disagreements that arise from poorly defined concepts or hasty annotations.
Yeah, this is also a great question. There is work on correlating agreement, and I could point you to one study, but I need to find it out. So there is some little work in this direction, in fact. But more needed, especially across NLP and vision task, I would think.
Thank you. And the last question for today is from Yanai El-Azhar. Any thought about how to expose predictions of such proposed models where more than one label is possible to users and downstream tasks?
Yeah, that's also a great question. How to expose predictions. So are you thinking about showing? So I think there is two parts in this. One is, in fact, when we do build pipeline models, we often still propagate the one label forward, right? If I think about the typical parsing with post tagging example in good old times where we still use post tags, for instance, but there has been a little bit work shown that you could be better off in keeping this ambiguity in the post tag for parsing, for example. So I think this is something in if you think about the pipeline, that perhaps is more, old way by now, but could be very beneficial to revisit even in neural days, right? Because now we have different ways of modeling it. But this might not answer your question. You're more about to show it to users. Why not, right? Why don't we show the system's distribution, especially for very sensitive tasks or tasks where I think that's done, right? That you show how confident the system is in different labels where there is a human then doing something with this label, right? It's taken as an input for some decision. It's not deciding for the user. Then it will be very important. But I think especially in those cases, currently we train with softmax and we disregard these distributions where there is a lot of information. And especially in these cases, it will be very important to keep that for showing down the line to the user, in fact.
Can I follow up on that? Do we still have some time?
Yeah, sure.
Briefly, we are already in the break, actually.
Okay, I'll make it. So in the example from Parvik and Tom, where the paper you mentioned of the inherent disagreement. So when there's more than two models, it means that, or one model, it means that there could even be contradictory answers. Like in analysis, you can have both entailment and contradiction. And this by itself can be maybe a bit confusing to users, right?
Yeah, that's a good point. That's true. But maybe, it factors into this problem of modeling the user, right? And the social cultural aspect. So sometimes there is an interpretation which is I think, effectively plausible in some culture or universe where it's contradictory in other cases. So it could be confusing, but I think there is more to be, I think there is value to this effectively. But we need to know why the disagreement appears. If we understand why, then we could have better informed measures on when to show what even.
All right, thank you very much, Barbara. Given that we already have a break, I defer the comment by Sandro in the Zoom chat to you, and maybe you could talk during the break.